All right. Hello, everyone, and welcome to our second workshop of the quarter on advanced graph theory. But before we go to the workshop, let's do a raffle based on the previous workshop and the contest that we had over the week. For those who don't know, each week we are going to have a raffle, which is based on physical raffle tickets that I'm going to give out for your answers to my questions. Also, each solved problem on the contest that we have weekly gives you another entry to the raffle. And if you fill out feedback form, you get another entry to the raffle. Okay, let's move on to the workshop. Here is the agenda for today. We'll start with a quick review of what we learned last time on what a graph is, what is BFS, DFS, and some other topics. Then we will move on to new stuff like directed acyclic graphs, trees, what are they, some examples, and finally we'll move on to topological sort and solve an example problem based on that. Okay, so before we jump into topological sort, let's do a quick recap on graphs. I'll click through these slides pretty fast, but feel free to stop me anytime if you have any questions or concerns. So what a graph is? Well, it's a set of vertices and edges that represent relationships between those objects. If two vertices are connected by an edge, we call them adjacent, and each vertex can have a degree, which means the number of adjacent vertices that it has. Another important concept in a graph is a path. Essentially, it's what you think it would be. It's a collection of vertices that are ordered and each connected subsequently that shows a path from one vertex to a different vertex. Some paths are cyclical, and they form a cycle, or also called a circuit. Well, essentially, it's exactly what you think it is. It's when the path starts and ends at the same vertex. So far, we've been talking about undirected graphs. There are other types of graphs, for example, directed graphs. Here, instead of edges, we draw arrows, and arrows represent a directed relationship between two vertices. In this case, we also define a degree of a vertex. We have in degree and out degree. In degree is how many edges are pointing to a given vertex, and out degree is the number of edges pointing away from a vertex. All right, does anyone have any questions so far? Okay, so graphs can get huge, and they can represent various different things. You might need to build a graph that's not given to you in the problem statement. You might need to come up with some algorithm that uses graphs, but the input doesn't appear like a graph. So we need a useful way in programming to store a graph. So we'll show an example in C++. So far, there are two main implementations for storage of graphs: adjacency list and adjacency matrix. Adjacency list is an array of vectors where each vector or list is stores all adjacent vertices of a given vertex. So, for example, this could be an example of adjacency list. So we see that vertex 0 is adjacent to vertices 1 and 2. In C++, we use an array of vectors, and you can add vertices and connections manually to those arrays. Another useful way to store a graph is adjacency matrix. Essentially, this is a 2D array, and you place 1 on the intersection of if row and j's column, only if and only if there is a directed edge coming from the vertex I to vertex j. You store 0 otherwise. So one example of such matrix could be here, and we can clearly see that it's an undirected graph because the matrix is symmetrical against the main diagonal. In C++, we can store them using 2D arrays and manually adjust the values of cells in the arrays, so setting them to 0s or to 1s. As you solve more and more competitive programming problems, you'll get more familiar with how to implement adjacency lists and adjacency matrices, and you'll figure out which one is more useful in certain cases. However, there is a general concept of what are adjacency lists and matrices are good for and what they are not that good for. So, for example, adjacency list is very space efficient. However, it's pretty slow if you need to check adjacency between two vertices because you need to iterate through the entire list or vector. However, on the other side, adjacency matrices, while it's very space inefficient because you need to store every single connection, it's really quick and easy to check adjacency between two vertices. Okay, any questions so far? So we just covered what a graph is. As I said, graph can get huge, can get really large, and we need a helpful way to go around every vertex in a graph. There are two main traversals that exist, breadth first search and depth first search. So let's go over the breadth first search first, or also called BFS. So the idea of BFS is that we start at some vertex and explore all its adjacent vertices, then explore all of their neighbors, and so on. So just like it's shown on this small diagram, you first explore the root vertex, and then explore its neighbors, and then their neighbors. For implementing BFS in code, we usually use a very useful data structure called queue, or also called first in, first out data structure. First in, last out data structure. Queues exist in standard C++ library. You can declare a queue like this, and there are some useful operations. For example, adding a number to a queue, receiving the first element of the queue, removing the element, and checking if the queue is empty. BFS itself is a very simple algorithm. All you need to do is create a queue, add the starting vertex into the queue, and while there are still vertices in the queue, you need to take the front vertex of it, put all of its neighbors in the queue, and mark them as visited. And repeat that as long as needed while there are still vertices in the queue. Here is the example code, how you can implement queue in C++. I'll not focus in detail on the implementation. You can always reference this slide. By the way, the link to the slides is right here at the bottom of each slide, so you can follow along. Okay, so this was breadth first search. And another useful traversal algorithm is depth first search. The main difference is the order of traversal. As opposed to BFS, in DFS, we start at some vertex. However, this time we explore as far as possible along one of the branches, and then backtrack and explore a different branch and a different branch. So the order might look something like this. You explore one of the branches of the graph, and then you come back to you backtrack, you come back, and then you explore another branch and another branch. In this case, similarly to BFS, we use another data structure called stack. Stacks also exist in C++ standard library. This is how you declare a stack of integers. You can place a number onto the stack. You can retrieve the first element of the stack and remove the element or check if stack is empty. However, while its implementation is somewhat similar to BFS, if you're thinking about iterative approach, there is another approach that you can take called recursion, which makes the coding part much more easier. So for those who are not familiar with it, recursion, in short, is an occasion, a process in which function calls itself directly or indirectly. So for example, if you want to calculate n factorial, what you could do is start from 1 and then multiply by 2 and so on until n in a for loop. However, you can also simply write these 4 lines of code where you say that factorial of n is essentially n times factorial of n minus 1. And then it will create n subsequent recursive calls to the same function. This same approach applies to DFS. Let's say we start DFS from vertex 1 and get into branch that starts with vertex 4. Here, we can look at this graph as if all other vertices do not exist. It's just 4, 5, and 6. And call DFS again on vertex 4, then on vertex 5, 6, and so on. This is an example code, and as you can see, it's much shorter than the one of BFS. because it uses recursion. Does anyone have any questions so far? So if there's no questions, I have a question for you. So BFS cannot be implemented recursively, while DFS can be implemented recursively and iteratively. Can someone tell me why is it only possible to implement BFS iteratively and not recursively? It's a very simple answer. Don't overthink it. Any ideas? Yes?
Because in DFS, you're going all with the and then you're searching backwards, and the other one you're implementing.
Yes, yes. Yeah, essentially, okay, this is Raffle for you. Please put your name and give it back to us to enter the Raffle. But essentially, you're right. The main difference is the order of traversal. So while in DFS, you just explore all the neighbors of certain vertex, then its neighbors and its neighbors. Here, the order of traversal allows us to apply the recursive approach. And that's why I like DFS more, because it's much easier to code. And if you only need to visit every single vertex without any additional assumptions or any additional goals, it's much easier to use DFS because you can use recursion. All right, this was the end of our review, and let's go to new topics, and I hand it over to Akash.
Hey everyone, this is all going to be new topics. So if at any point you think I'm going too fast or you have a question, just please raise your hand or shout out your question, and I'll be happy to pause, go over any misconceptions or any other questions you might have. So trees are graphs that have the minimum number of edges you need to connect everything. They're graphs that have n-1 edges. That means you are not going to have any cycles. Trees are usually used to represent any hierarchical data structure. For example, in your file systems, you'll have folders inside other folders, and inside those folders, you'll have files. That is an example of a hierarchical data structure where you would use a tree. There are other examples, for example, like a course requisite graph where you need like some course to do another course. Basically anything where you would need to do something in a certain order, oftentimes you can represent it as a tree. Because this case shows up so much, it's useful to study trees in a little bit more depth, even though they are, again, just an example of a graph. And you could use anything you've learned before with graphs, such as BFS and DFS, with trees as well. So there's some terms we need to know for studying trees. Again, like with a graph, you're going to have nodes. But the thing with the tree is you're going to have what's called a root node. A root node. So like visually, the root node is basically the top of the tree. From the top of the tree, you can access any other node simply by going down the edges. The parent of a node is any node that's directly above it. And if you expand that a little bit more, an ancestor of a node is any node that's above it. Not directly, it can be one edge, two edge, 1,000 edges above it. As long as it's above it, and you could go to it by just following an edge upwards, it's an ancestor. The opposite of a parent would be a child, any node that's directly beneath your current node. And a descendant, again, is just, instead of directly beneath, any number of edges beneath. And finally, a leaf node is any node that has no children. You can imagine all of these nodes to be like the bottom of the tree. Once you hit it, it's a dead end, you can't go any further. For example, if we were running DFS on a tree from the root node, the leaf node is what you would hit when you go back recursively, since you can no longer go any further. So this is where we're going to do our first example problem. Here's a contest link, and you can see the problem for yourself. But we also have a worksheet if you want to go through the problem and collaborate with your peer. It's going to have what I like to call starter code, where you don't have to worry about a lot of the heuristics things like inputting the code or outputting it. You just need to understand like the algorithm. So if you want to go and collaborate with your peers on the worksheet on this problem, we'll go over it, like talk about the problem description in a bit. But if you want, just read through the problem first and see how you can start. everyone has a problem up, I'll just go to like, this is basically just a copy of what we have on the worksheet, but these are like basically the steps that you'll use to solve the problem. You'll want to fill in all the to-dos on your own using like whatever algorithm you choose, but this should get you started on having a correct solution. One observation I had was it's like every node has to be numbered 1 through 100. It's not immediately clear why that's helpful, or even if it is helpful, but it always helps to just note things about the problem statement to get a better understanding of it. Yep.
I was just gonna say, it seems like you could either, it would probably save time and be just in general better to do like an adjacency type of thing. But it seems like you could also do this by just like manually going down, finding a number and like without like initializing a graph structure, but that would probably take a long time and stuff. So,
Why do you think that would take longer?
because it might require more looping, maybe. I'm not sure. Like looping through finding the node value and then finding the node that connects to the node. I don't know.
I think that's a step in the right direction. I guess just a clarification about the problem that kind of lends itself to your solution is that in each line, when you have integers a, b1, b2, and so on, a is the node that's directly beneath b1, b2, and b3. So I guess for your solution, just going straight down, it tells you the node right underneath.
So could you just go down to just search for I guess the node 14. That is one of the B values. It's not A, but like look for 14 and one of the B values on the, I guess, the right, and then find its corresponding A, and then save the A now, and then go down. Find the A that is, or find the B that is corresponding to the A.
That would work, yeah.
Okay.
All right, did everyone hear? Sorry, what's your name?
Carson.
Carson, did everyone hear Carson's solution? All right, let me just give a recap of it then. The idea is, and we're going to consider the smaller test case just because it has fewer nodes. In this example, 31 is the starting node, this one right here. And I put the tree upside down because just it represents like typically what we see if we look at like a data structure tree. But basically Carson's idea is just following your starting node straight up until you reach the top of the tree. And the problem lends itself to it because in each of our lines of input, it tells us what is directly above it. For example, in this first line, it tells us that 14 is right above 5. In this line, it tells us 5 is right above 9, 11, and 2. In the third row, here it tells us 1 is directly above 31, and so on. So the problem lends ourselves to just going straight up a node and basically go until we reach the top of the tree. So I guess our problem is then just becomes find a path from the starting node to the root node. So for example, starting at 31, we go to 1, then 11, then 5, then 14. So the strategy just becomes traverse the tree by starting at a node and going to the parent of each node. Using the terminology from earlier, all that means is going from a node directly upwards. When you go straight up, you go to the parent of your node. And I guess the main way we would do this, instead of storing our entire graph with an adjacency list or a matrix, we can just have an array of integers where we store the parent of each node. And for the root node, where we don't have a parent, we can just say -1 to indicate that we've reached the top and we can terminate our program. So here's how the code would work. If you're creating your graph and we want to go with our solution of just storing the current parents, all we need is just an array of integers that would store the parent of each node. To initialize it, we would initially have each node, its parent set to -1, indicating that it doesn't have a parent yet. And when we update our graph, what our, I guess, parse input function has done is it gives the first integer as the parent of the rest of the integers. So we can just update that with the array. The parent is the first integer. We indicate that by using input, open bracket, 0, close bracket. And is everyone familiar with this kind of for loop notation? Just a refresher, you have your regular for loops where you have for int I equals 0, I is less than something, I plus plus. But when you're dealing with vectors, there's a cool syntax you can use called where you can just auto child or like auto the name of the variable and then the vector you're going into, and it will just go iterate through all your like integers in the vector. So for example, we would just iterate through all the integers in input, call that variable child, and then do whatever we want to do with it. In this case, we're going to set the parent of each node other than parent to parent. Any questions about that? That syntax is not like, it's not as common as the other one. All right, at this point, it's important to note that every node now has a parent except the root node. The root node is the only node in the tree that's going to have a parent of -1. So for finding the correct path, we'll just set a current node counter to start. And while our current node is not -1, that means while we haven't reached the top node, we're going to add the current node to our path. That's one of the nodes that we've crossed while going up. And then we're going to go to the next node. By going to the next node, what we mean is going up. And what we mean by going up is going to the parent of the node. So we say cur or current equals the parent of your current node. Are there any questions about this? And I thought this problem was a nice problem because it tells you one of the major benefits of trees. Unlike graphs, you don't need to store, there are not many edges you need to keep track of. There are only n-1 edges. So oftentimes, while you can use an adjacency list or an adjacency matrix, you can also store a tree just by keeping track of its parents. In this case, you can keep track of its parents while going up. While going down, you would still need an adjacency list because when going up, there's only one choice, but while going down, you can branch off in many different ways. But it's nice knowing that one of the specific conditions of a tree, that it has so few edges, can help us solve a problem in a much more efficient and elegant way. One last thing we can do with tree problems, and don't be scared of this. This will be covered again in one of our future workshops on recursion and dynamic programming, is we can solve a lot of tree problems doing recursion. For example, let's take this example problem. We're given a tree. You want to go to each of its nodes and take the sum of its values. Well, one way you can do this is by doing a DFS. You search through the tree, going to each dead end. And when you reach a dead end, you take that value and add it to a current sum. But another thing you could do is use recursion and split our tree into subtrees. For example, we have this entire tree that's rooted at 8, but we can split this into two subtrees, one rooted at 3 and the other rooted at 10. We can solve the subproblem for both these separate trees and then add them up. Now, we usually have 3 steps for solving these problems. You don't need to follow these, but they give you a nice way of systematically solving recursion problems. First, you want to figure out what happens at your base case. So in our smallest unit of a tree, when you go to the absolute bottom, you want to know what you do at that case. For a raffle ticket, does anyone want to tell me what you do when you get to a leaf node or your smallest possible tree? For this problem specifically. You don't have to overthink it. It's pretty much just a declaration of what the problem says. What you want to do in this problem is take the sum of your leaf nodes. So when you reach a dead end, when you're only at the bottom, you can't go any further. You are at a leaf node. So for example, if we kept traversing and went straight to this one, and we had no more subtrees to consider, what you would do is just add 1 to the current total, because it's a leaf node. We want the sum of the leaf nodes. So our next step is pretending you know the answer for like the problem of subtrees and thinking what you would do to combine it. For example, if we had, in this case, our left subtree has a sum of 1, our right subtree has a sum of 4 and 7. Can anyone tell me what the sum, ignore the coloring, can anyone tell me what the sum of the leaf nodes is in the left subtree, where this subtree right here gave you a 1, and this subtree gave you 4 plus 7, or 11? Well, in this case, if you know the sum of your leaf nodes in your first subtree, and you know the sum of the leaf nodes in your second subtree, to find the sum of the leaf nodes for the entire tree, you would simply add them up. Each one of your leaf nodes either has to be in the left subtree or the right subtree. So its sum is calculated when you do each individual subtree. And lastly, you just use those 2 steps basically to solve your problem. In the left subtree, so far we've calculated a 1 plus 4 plus 7 for each of the 3 leaf nodes, which gives you 12. When you iterate through this right subtree, you'll get a sum of 11. And combining this, you get your 12 on your left subtree plus your 13 in your right subtree, which gives you 25. In this specific example, we basically only had left and right subtrees, but this doesn't have to be the case. A tree can have like 10,000 subtrees, and you could calculate it for each and every single one, and still use your recursion somehow to combine the answers. Again, this will be covered in more depth in a future workshop when we talk more about trees and deep dynamic programming on trees. Are there any questions on trees so far before we go into the next topic? All right. If there are no questions, we'll go into the second topic, which is directed acyclic graphs. This will basically be the topic for the rest of the workshop. And so we'll just start with the definition. So we've seen what directed graphs are. A directed graph is basically a graph with edges where you can only go in one way. And we've also seen what cycles are. A graph with a cycle is any graph where you can start at one point and take a path and end at itself. What we define a directed acyclic graph as is a directed graph where you don't have any cycles. For example, in this left graph, you can try to find a cycle, but you're not going to find any. There's no way, for example, to get to leave this node and then come back. There's no way to leave this node, like, period. And there's no way to get back into this node. In general, a directed acyclic graph, you're just not going to have cycles. Conversely, we have this right graph, not a directed acyclic graph, because there is a cycle. You can go from the bottom left to the top right, back to the bottom left, and you're going to get a cycle. Because the name is kind of a handful, it's pretty long, we simply just call it as DAG. It's an acronym for directed acyclic graph. So for a Raffle ticket, take a minute, look at these 3 graphs, and please tell me which one of these are, or if there are multiple, which of these graphs are DAGs, or directed acyclic graphs. Yep. The first and third one. Okay. This first one, it is a directed, it is a DAG. The right one is not. Can you see why? Oh. It's kind of annoying that this node is right here, because if you had it out, it would like clearly be a circle. But yeah, you get a, do you see it? You get a cycle from those 5 nodes. But like the left one is your directed acyclic graph. And again, a directed acyclic graph has no cycles. As you can see here, it takes a while to check if a directed acyclic graph doesn't have cycles, because you have to go through like every possible iteration. It's a lot easier to check if a graph is not acyclic, because you just need to find a cycle. It's harder to prove that a graph is not cyclic by hand, But there are algorithms that we're going to learn that will help us determine if a graph, a directed graph, has no cycles. Before we get into that, I just want to quickly preface that with what kind of things you can do with directed acyclic graphs. Directed acyclic graphs, or graphs where you have no cycles, have a lot of applications. For example, when I'm sure if you have like courses and prerequisites, you always have to do one course before another, before another, before another. And it'd be really silly if a course prerequisite graph was cyclic, because it'd be like you needing to do CS31 before CS32, and then you needed 32 to do 31. Like you could never do any of them. So in situations like that, it's natural for your graph to be acyclic. So in application, they show up a lot. And so it's important for us to know when a graph is acyclic, and if it is, what we can do with it. So cycle detection. How do we know if there are any cycles in a graph? Recall, a cycle is simply where you have a path that starts and ends at the same node. And we have an algorithm for detecting cycles. This uses DFS. And the basic premise is that you start at a node and start traversing the tree. If you ever hit that node again, it represents you having a path that started at that node because you started the DFS there, and ending at that node because you arrived at that node again. Now, there are certain steps we need to be careful of, but that's the basic premise. You run DFS on a tree, and if you hit the node you started with again, you have found a cycle. So we're going to start at a node, and in your regular DFS fashion, you would set that node as visited so that you don't follow the same path over and over again. Once you do that, you would find all the connected nodes, and in DFS fashion, call DFS on them. For example, here we go to our bottom node, run DFS on that. If DFS terminates on one of your nodes, you have an additional step. This part is different from DFS. For cycle detection, what we do is we change the status of the node from visited to good. What good means is there's basically no cycles involving this node. If we've run DFS on it and we weren't able to find a cycle from that node, that means we can eliminate it during our search for cycles. And we would continue from our process of DFSing on other nodes. We'll go to the bottom left, then go to the top node, then go to the right. Like normal DFS, from your bottom right node, you can't go any further. Your DFS terminates. You set this node as good. The top one has also the one right above it has also terminated. You set that one as good. And then you run DFS from this node now, the other node. You go down. In this part, one important thing to note is you don't visit any good nodes again, because if it's good, you've already confirmed that there are no cycles involving that node. So while in a regular DFS, you might go right to that blue node, you've already confirmed there is no cycle. So it's just time efficient to never go to that node again. In this case, we go straight down. There's nothing else here, no cycle. You set it to blue. This is the one above it to blue. And then as our last part of DFS, we go here. That node is one that we've already visited. That's where we started our DFS from. And if we're able to reach it again, we've detected a cycle. We started at that node, we ended at that node. There's a cycle in this graph. If this ever happens, you can terminate your program and say with confidence that you have detected a cycle. But if you've run through your program and you've never visited a green node or a visited node again, you can say with confidence that you have no cycle, that your directed graph is a directed acyclic graph. So in code, I've written these 4 steps here. You set your current node as visited. You call DFS on all your connected nodes, i.e. the ones that are not visited or not good. If the node you're going to is visited, you've detected a cycle. You can return, in our case, false. We return false if there's not a cycle, and true. Oh, false if there is a cycle, true if we haven't found one. And then once you've finished DFS for that node, you will set the status of that node to good. Again, good means we haven't detected any cycles from that node, so we don't need to consider it ever again. In code, we set the current node as visited, and we iterate through each of the nodes that are connected to it. That's what we mean by auto next : graph node. We're iterating through all the nodes that can be accessed through our current node. If the node has already been processed, we skip it. That's what the continue syntax means. You skip the rest of the for loop and go back to the start with your next node. If it's already been visited, you found your cycle, and in this case, we return false. And if you found a false in any of your next nodes, when you run DFS on any future nodes, and there's a cycle in that one, you found a cycle, you can return false in this one as well. And after we've run all this, if we've never found a cycle, we can set this node to be good. We can set the good of this node to be true because you haven't found a cycle, and you can return true, knowing that from this node and anything you could access through this node, there was no cycle. Are there any questions about this? The premise makes sense, right? It's just DFS, and if you find the node you visited before, you found a cycle. But in application, it can be pretty confusing. Like first, intuitively, it feels weird to have a visited and a good. Like if you visited before, like shouldn't it not matter? But are there any questions about this? All right, sweet. Now that we've done this, you can confirm if you have a directed graph that you can confirm whether it has cycles or not. So one might ask, well, now that you've confirmed that a directed graph is acyclic, what can you do with directed acyclic graphs? And that leads us to topological sort.
All right. So this is going to be the last part of the workshop, and we'll talk about topological sort. But before I go into implementation of the sort, let me give you a motivational example. So here you can see a requisite structure for computer science and computer science and engineering majors at CS department. And can you please take a look at it and tell me if there's anything specific, any properties that you notice about this graph, anything that you might find interesting or related to the topics that we covered in today's workshop. Yes, that's a good point. There is a path because essentially, when you plan out the courses that you're going to take, you want to make a 4-year plan. You want to make a 4-year plan so that all the prerequisites are confirmed, are followed. So, well, first thing that we notice about this graph is that it's directed and acyclic. If there was a cycle, then we would be stuck in this graph forever and taking CS courses in CS departments for eternity. So there is no cycle, and also directed because there is a certain relationship between certain pairs of courses. You need to take CS 180 to take CS 170A and so on. So let's just follow this set of questions to bring more clarity about that graph. So is there a natural order to this graph? Well, yes. As Arnold said, basically we want to find a path, or we want to find a way to sort or order these classes so that we do not violate any prerequisite requirements. Is there an order to take classes that you don't violate? Right. So this is basically what we just talked. So, well, an example of that, an intuitive example is if you're taking CS32 right now, for example, you probably have taken CS31 already, which is a prerequisite course for that. So you want to take it first, and then all the required courses where CS32 is required are going to follow next. So there is a certain order, and that order is called topological ordering. So this is the definition of the ordering. A topological ordering of vertices of a directed acyclic graph is such an ordering where if there is a directed edge from vertex I to vertex J, then I should come before J in that ordering. Notice that here numbers 1, 2, 3 through n do not really mean any kind of prevalence or ordering. These are merely to indicate the vertices. This could be letters A, B, C, D. This could be class names, just like in our previous example. So another thing to note is that topological orderings are not unique. Just like there are several 4-year plans that you can take, there are several orderings for the graph that can follow the topological rule. So does anyone have any questions about the definition so far? Okay, so can someone tell me why exactly, why do we define topological sorting for directed acyclic graph? Why cannot we just define for graph in general? Is there something special about that type of graphs that allows us to do the sorting? To lay out the vertices in one certain way? Well, no worries. Essentially, this lies in the definition of the DAG itself. It's acyclic. If we had a cycle, then there is no way to determine which course goes first, because there are two paths that lead from one course I to course J and back from course J to course I. So we don't know the order that we should take that we should use to place the vertices in a sort. Okay, so knowing the definition, let's come up with an algorithm for such ordering. So let's go through the algorithm first and then consider it on a particular example. Well, just like in DFS, you start from a given node and run our regular DFS, but not exactly. We change it slightly. When we get to a leaf node, which, if you can remember, are these nodes 1, 4, 7, 13, we add it to the topological ordering and continue. Once we finish adding all the nodes of the children, let's say nodes 4 and 7 are added already, then we can add node 6 to the ordering as well, while continuing doing DFS recursively. And just like in DFS, we mark nodes as visited and keep track of that. So if this doesn't make sense just yet, that's all right. Let's look how this algorithm works on a particular example. So let's say we're given node 8 and we start from 8. Just like in DFS, we go along one of the branches. Let's say we go towards the left branch. We go to node 3 and to node 1. Well, now node 1 is leaf node, so we add it to our topological ordering. We backtrack to node 3, continue to a different branch, go to node 6 and all the way to node 4, just like in DFS. Node 4 is a leaf node again, so we add it to our topological ordering. We continue to node 7, we add node 7. Now, since we covered both children of node 7, we can add, of node 6, we can add node 6 itself. Same happens to node 3 until we get to the root node where we started. And we go to the right branch of node 8. We continue to node 10, 14, 13, go all the way down to the leaf node. Now 13 is the leaf node, so we add it. All children of node 14 are added, so we add node 14, node 10, and node 8. And this is how we get the topological ordering of this graph. Well, while you might think that this is a great algorithm, it still might be unclear why exactly we do things this certain way. Why do we use DFS and not BFS? Why do we add leaf nodes? Why exactly we follow these rules? So there is a certain intuition for topological sort. Well, as you might have noticed, topological sort has certain recursive nature. If you just focus on the left branch of node 8, nodes 1, 3, 6, 4, and 7, if you sort those nodes, solely those nodes, you can treat it as a separate chunk of your topological ordering. And as you can see here, indeed, it goes all as a separate chunk. So it has certain recursive nature. So that's why we use DFS and not BFS. As you get to a leaf node, we know that it must be among the last nodes in the order. Indeed, leaf node has out degree 0. So there's no potential nodes that will have an arrow pointing from leaf node to them, meaning that they can go anywhere in the ordering, might as well go at the end. So we can safely add them to the ordering. And finally, if all children of a node are added to the ordering already, they kind of work as leaf nodes for us, because we know that nothing prevents us. We there is no pattern that prevents us from adding that node itself to the ordering. So for example, as you can see here, nodes 4 and 7 are added already, and those are the only nodes that node 6 points to. That means those are the only nodes that would prevent us from adding node 6. Now, as they are in the ordering already, we can add node 6. And that works for any node in the graph. All right, let me summarize this idea in a bit more detail. So we start at a certain node at a given node of a DAG or a tree. Notice that we want to start from a node that has in degree 0. Can someone tell me why? Yes?
What is in degree?
Oh, in degree is the number of adjacent vertices that have arrows pointing to the node.
So that's the root node?
Yes, well, in a tree, it's a root node. In a directly acyclic graph in general, it's simply a node that doesn't have any other nodes pointing to it, meaning that that first node can go right into the topological ordering. If you want to cover all possible nodes in a DAG or a tree in our ordering, we want to start from a node that doesn't have any prerequisites itself. If you want to make a 4-year plan, we would probably start from CS31, which doesn't have any prerequisites itself, rather than starting from CS33 when it has prerequisites CS31 and 32. Same works for graphs. As we choose the particular node, we perform DFS on that node as usual, but at the end of the DFS, we can append that node to our topological ordering. Essentially, when we come to an end of the DFS function, this means that we either got to a leaf node, which doesn't have any children itself, or we covered all the children that it has before getting to the end. That means that we can safely add it to the ordering. Finally, as you might have noticed on the previous slide, we didn't get the topological ordering exactly. We got a reversed topological ordering. So the last thing that we need to do is simply to reverse the vector that we got. And there are multiple ways you can do that. For example, in C++, there is a function reverse in algorithm library that you can use, or you can also do it manually, depending on the needs of your program. All right. Does anyone have any questions about topological sort in general? If not, let's look closely at the example that I just provided about course prerequisite graph and see how we might program this kind of problem. So for starters, we need some way to keep track of a class and its prerequisites. So the best way to do it is a data structure called map. Essentially, map is a collection of key value pairs where key values are unique and where keys are unique and values can take any particular value, any vector or anything. So for example, this is the way to declare a map where keys are of type string and values are of type vector of strings. This means that when you add a key value pair to your map, your key, this string, should be unique, and your value, which is a vector of strings, can be anything you want. C++ standard library has this data structure. For example, you could use unordered map or map. The only difference is that underneath, they use a different data structure. So for example, unordered map uses hash table, which makes it really fast. You shouldn't worry about that because on a high level, you can simply use these operations to work with a map. This is how you declare it. And on the third line, you can see that we add a key value pair where key is food and value is a vector of apple, banana, cookie. Just like in a regular vector or with regular bracket notation, you can access the value of the key food. And finally, you can also check if the map is empty or full. Does anyone have any questions about the implementation of map in C++? If not, let's define a problem statement. So let's say you're given this type of input. The first number represents the number of courses that we are considering. So in this case, it's 5, and the courses are CS31, 32, 33, 35L, and CS111. And the following 5 strings go in a certain format, where the first value is the course that is prerequisite that we are considering, and after the column are the courses that are prerequisites for that course. So for example, if you look at the 4th line, CS35L requires courses CS31 and CS32. And the final line has the course that we want to find out the prerequisites courses for. In this case, it's CS111. So let's just look at it conceptually. Can someone tell me what would be the output for this kind of input for CS prerequisite chart? If we input CS111, what would be the required courses for CS111 to take based on this input information? Anyone?
What's the question again?
So if we consider this kind of input, where these lines represent the course and its prerequisite courses, what would be the prerequisite courses for CS111? All of them. Not just those listed in the final line.
The
Yes?
35L, 33, 32, and 31.
Yes, yes, that's correct. Essentially all of the courses listed above it. And basically your output might look something like this. You'll first have to take CS31, 32, 33, 35L, and only after that CS111. Okay, so is the problem statement clear? We are given a list of directed relationships between courses, and we want to find out what the ordering is up to the course in the final line. If so, before we go to the worksheets, let's go over general implementation in C++ and some code that's already given for you. So for starters, we have include statements just like in the previous problem that we considered, but in this case, we also include an ordered map because we use it to store the graph itself. And then there are several global variables that we have. Well, first of them is our graph, which is a map of key value pairs where keys are strings, the classes, and the values are vectors of strings, basically vectors of classes that are required for that key class. We also have a visited array, well, visited map, which we use to check if the course has already been visited or not. This will be useful later for our DFS or Topological Sort function. And finally, we'll store our output in topo order vector. Basically, this is where we'll put our topological ordering. Any questions about the global variables that we have? If not, you might have noticed if you looked ahead in the worksheet, there is a function parse input. As you can see from the problem statement and the sample input, that the input is given in a certain way that it might be hard to process it in code. So we've given you this function that you can safely just copy and paste in your code and don't really worry about it. I will not go into deep details about how it works because our focus today is topological sort, graph algorithms, and not some basic string operations. What it does, it takes the input, one of these strings, and outputs a vector where the first element of the vector is going to be the first class in the line, and then the rest of the vector are the required classes that follow after the column. I think now we have all the building blocks that allow us to go to the main program. for implementation. So if you look at the back side of the worksheet, you will see two functions. Our main function, which starts from reading in some values and a bit of parsing input. And the second function is top sort, which is essentially a slightly modified version of DFS. So let's take several minutes and fill out the to-do gaps. A small hint is that the top sort function that we see at the bottom is almost identical to DFS function that was on the slides, with only one difference. All right, let's take a bit of time. Feel free to discuss the worksheet among each other, and raise your hand if you have any questions. An officer will come and help you. I'll move back to the slide with global variables, so it's easier for you to see which variables we are using. Okay. Hopefully you guys had a bit of a chance to fill out the to-do gaps. Let's go over them together. So this is how the main function would ideally look like. Well, essentially what you will do is you read in the number of courses that you're considering, and then for every course that you're considering, first you parse input that's already on the worksheet, and then you need to update the graph data structure to create a graph from the list of courses that you receive. The first course in the line is the key course. So this is the key for our map. So we access it using the bracket notation, graph input 0, and then we add to that vector, which is the value for that key, we add every single course that follows the column, essentially all the rest courses from the vector. After that, after we create the graph, all we need to do is create the top sort function, which we'll talk about in a second. And finally, after you run it, your topo order vector will have the ordering that you want to output for the user. So finally, the topo sort function, you might notice that it looks very, very similar to DFS that we covered at the beginning of our workshop. All you need to do is, just like in DFS, you mark the course as visited in your visited array, and then for every course, every adjacent vertex of the course you're considering, essentially for every course that's required for that course, you first check if it's already visited, because we don't want to go into infinite loop of visited courses. We check if it's visited or not, and if it's not visited yet, we essentially run the same function on it. Sorry, this is a typo. This should be top sort. So far, it looks just like DFS, these first 4 lines. And then the last line is what's distinct between DFS and topo sort. You add the course that you have considered into the ordering. Essentially, at this point, it's either a leaf node in our graph, or it's a node that has all of its children visited already. And we return. Does anyone have any questions about the implementations that we went over? All right, if you have no questions, there is a problem in this week's contest that only needs 2-line change from the course prerequisite problem solution that we just went over. So you can copy most of the code that I've covered today and change just 2 lines to get a solution for problem B on the contest. All right, if there are no more questions, we'll do a quick Kahoot. So the workshop part is over for today.